Welcome back. We're going to do example 7.2.1. Let x be the time that a manufacturing system is out of operation, and suppose that the cumulative distribution function for x is f sub x of x is 1 minus 4 over x squared, all squared for x greater than 2, and 0 otherwise. The resulting cost to the company is y is equal to x squared. If x is a random variable that depends on chance, well then y, which depends on x squared, also depends on chance. So y is a random variable, which means that y has a density and a cumulative distribution function associated to it, and we are asked to find the density function for y when y is greater than 4, and then to calculate the probability that y is greater than 5. We have in the previous video a formula that would give us the density function directly. We are not going to apply that formula. Rather, we're going to go through the derivation that's in the proof, because that derivation is a little bit more flexible for cases where the conditions of the proof are not met exactly. So let us introduce some notation. Let's let f, capital F sub capital Y of y be the CDF for y, and let's let little f sub y of y be the PDF. Now it is little y or little f that we are after. We're going to start with the CDF first though. And so f sub y of y, by definition, this is the probability that y is less than or equal to little y, that the random variable y takes values that are less than or equal to this little value y. Now y is equal to x squared, so we can write this is the probability where x squared is less than or equal to y. Now, if we just took the roots of both sides naively, we would, in this case, be right, but only because of a certain restriction in the domain. So we cannot just take the root of both sides without doing that justification. Now, we are told that x is greater than 2 and y should be greater than 4. Well, that point is exactly the point that's on the parabola. So we are on this part of the function here, and on that part of the function is 1-to-1, which means that it is invertible. It is increasing. And so because we are in this case where x is greater than 0, we may take the root of both sides and preserve that inequality. So we have the probability that x is less than or equal to root of y. That is exactly the formulation, that is the definition of the cumulative distribution function. But instead of little x here, we have root y, which means that in the cumulative distribution function, we are going to plug in root y. So this is equal to f sub x of root y. Now we have a formula for it sitting right here, so we can plug in root y. So that is 1 minus 4 over root y squared all squared, which is 1 minus 16 over root y squared. The root and the square cancel. I get y squared. So there is the cumulative distribution function. That's not what we're asked for, though we want the density. So we are going to use the fact that the density function is the derivative of the cumulative distribution function. Normally we calculate this one as the integral of this. We're going to go the other direction this way. So we want the derivative of 1 minus 16 over y squared, so we want that primed, which is the derivative of constant is a 0. This is minus 2. That minus 2 is to come down and multiply by minus 16, and so we get 32 over subtract 1 from the power y cubed. There is the density. Now that, however, is not a complete answer because we haven't given the support. We haven't given the values of y for which this is valid. So a full and complete answer is f sub y of y is 32 over y cubed when y is greater than 4 and 0 otherwise. So there is the full and complete answer for the density function. That's not all that we're asked to do, however. We're also asked to calculate the probability that y is greater than 5. So if we call this part A is done, and part B is here. So this is our part A, and part B, the probability that y is greater than 5. So the probability that y is greater than 5 can be obtained by integrating the density function. 5 is greater than 4, so we're in the correct place in the support. So we would integrate from 5 to infinity of f sub y of y dy, which would be the integral from 5 to infinity of 32 over y cubed dy. And 100%, if we did this integral and took the limit because it's an improper integral, we would get the right answer. There is, however, a quicker and easier way to do it that uses some work that we've done previously. The probability, so this is alternatively, the probability that y is greater than 5 is, we're going to use a complement rule. This is 1 minus the probability that y is less than or equal to 5. And that is super nice because that is exactly the cumulative distribution function that we have a rule for right here. So we can say this is 1 minus f sub y of 5. F sub y is the rule that we have right here, which is going to be, so 1 minus 16 over 5 squared. So those 1's are going to cancel out, and we're going to have 16 over 5 squared. 16 over 25 is the probability that y is greater than 5. So if you want to try it out and do this improper integral and evaluate this with a limit, you should get this answer as 16 over 25. Unless you are an aficionado of improper integrals, I have no idea why you would, when this is so much quicker and easier to do, especially as we have the rule sitting right there. In the next video, we are going to build on this result, and we're going to use the density function of y that we've calculated here, as well as lotus with the distribution of x to calculate expected values and check that both answers give us the same thing. See you in a bit.